Okay, so this video we're going to be talking about Prim's algorithm, but we're going to do Dijkstra's algorithm first. I was going to make a video. I kind of fell apart. I know I've done it before in Visual Basic, and that's about the only thing I ever bother to code in anymore. I've never done Python, and never done Python. I've messed with C++ some years ago, I think, and I've done Java. I hate them all. The only one I like a little bit is Visual Basic, in that a lot of times in Excel I can go in and click my way through most of the way through a program and then just go and clean some stuff up. Anyway, so I started messing with it. I saw one online. I could try to copy it, but I kept messing up on me, so I'm not going to fool with it right now. I think it's going to end up becoming part of my one of the projects. I know we have some software people, so I think I'm going to change my project a little bit this term and allow some of that as well. Okay, so T to be a graph with vertex A and no edges. Okay, cool. So initially you're just going to have vertex A. Okay, and then V of T is the set of vertices of T, and E of T is going to be the set of edges of T. So what that means is this. Here's our graph. This is our graph T. This is the graph. Okay, and so here we have a... I'm going to go ahead and draw these in. And I'm going to go ahead and label the edge lengths here as we get going. No, I already did 16. Let's try something different. I don't know. I just want to do something different. Doesn't really matter, but I want to try something different. There we go. Now, it doesn't really matter which one you start with, but we're just going to start with A. Okay, so initially what we're going to be doing here is we're going to be starting off with A. Okay, we're going to have a set of vertices. So our set of vertices is V of T is equal to A, B, C, D, E, F, and G, and H. Okay, and then what would they switch? I forget what they use for their variable here. E of T is the edges of T, obviously, E of T. And so the edges are, and they're not labeled here, but you could go in and label them E1, E2, and so forth. Okay, it's great. Or you could define them where they go to. We have an A to B, a B to C, and so, or A to C, and so on and so on and so forth. Okay, those are what our E of T's are. Now, we are going to start off with. Oops, what just happened here? Come on, magnify yourself, you hippie. No, don't draw on the picture. That's ridiculous. Stop it. Stop it. I just want to make you bigger. Bigger. Just get... There we go. Cool. All right, now. So for all vertices in G except A, you're going to let L, the length of that, equal. So L of A is 0. So what does that mean? You're going to keep track of, as we go along, you're going to have a list like so. And you're going to have the actual vertice, oops, the vertex here. And then you're going to have, this is, if you want to look at an example of this, they do an example for you on, kind of, on, they set theirs up a little differently than I do, but I don't know, it's fine. You can do a vertex, you can do a distance here, and then a column from what vertex. Okay, and so A is 0 distance from A. Okay, all the rest of them, you're gonna put infinity in there. Okay, and the idea is they're an infinite distance out right now. That part is neither here nor there as we speak. but as we move along, it's going to become a bigger deal. So as I come down to this, I start drawing this out. I have A, and of course I have B, C, and D. So I'm going to kind of draw them up thusly. And where did my picture go? I forgot where my picture went. Is it up here? Yes, there it is. So A to B is 10, obviously, because that is 0 from A to A, and then from A to B is 10, so 0 plus 10 is 10. Cool. From A to C is 5. Again, that's 0 plus 5 is 5. And then, of course, A to D is 16. Notice we didn't fool with the other ones, so as far as we're concerned, they're still infinitely far away. Now, later on, it's going to become a situation where, like, how many paths can you use to get to E? A lot. How many paths can you use to get to G? Well, quite a few. So at those points, it won't be so obvious anymore because we're going to have to take into account these other distances and go, okay, is this the shorter path or is this the shorter path? Now, one can see that to get to E here in a few minutes, which we're not going there yet, but to get to E, well, actually, we are going there pretty much next, I guess, aren't we? To get to E, clearly, you can see that you're going to go 0 to 0 here, and then it's going to be 10 plus 9 is 19. 5 plus 19 is 24. Oh, good gosh. And then you clearly 25 going that direction. Okay? And so then it really comes down to, let's see what happens here. So how many ways can I get to E? Well, I could go from A to B and then from B to E. That's 19 total. So we'll write that down. So that is A to B to E is 19. A to C to E is going to be 24. And A to D to E is going to be 25. This is clearly the best one. Okay? And 19 is obviously less than infinity. So we're going to replace that infinity with 19. And where did we get to E from? We got to E from B. Okay, so we put that over here like so. Oh, where did we get to these guys from? We got to them from A, clearly. Okay. Nice. And so off we go from here. Okay. Who's next? Well, F is next. All right. Well, listen, how many ways can we get there? Well, we could have gone from A to B to F, A, B, F, or A to B to E to F. Okay. And of course in a variety of other ways, but we need to start from places we've been. You see, we need to be from places that we've been. So to get there from where we've been, A to B to F is 28. A to B to E to F is 1933. Okay, that is the best that we can do, either to go from B to F or from E to F. Those are places we've been. Now you're like, well, I can get there from H as well. Yeah, hold your horses. We'll get there in a few minutes. Okay, we'll talk about that. Okay, we'll talk about that as we go along. Okay, so we'll see what happens there. Okay, so currently our next best algorithm there is to use that component.